Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello, Alexander. Thanks so much for joining us on the podcast. Such honor to have you.
Yeah, thank you so much for inviting me. It's really an honor to be here.
So maybe firstly, I would ask you how you'd like to define yourself, maybe for people first time listening to you. I know people know you, but maybe you can define who you are. Yeah.
Of course. Yeah, so hello, everyone. My name is Alexander Amini. I'm a PhD student, PhD researcher at MIT in the CSAIL, the Computer Science and Artificial Intelligence Laboratory. I do my research with Daniela Roos, Professor Daniela Roos, and my research focuses on deep learning for robotic control. And specifically, I have a few interests within that field that really excite me a lot. So I'm a roboticist, but within that subset of robotics, I really care about how we can build robots that can be robustly deployed into the world. So what does that mean for robots? Typically, one way that I like to think about this is how can we have robots that can interact with humans, and humans can understand when we can trust the robots and when we should not trust the robots. And for deep learning systems, this is a huge issue because a lot of these systems are often considered black boxes. So understanding when we, the humans, can really trust the system is of huge importance. And I would say that this is really exciting today more than ever for me because of the advances that we're seeing in autonomous vehicles and robots that are actually reaching society and touching humans in a way that we've never really seen before.
Great. So maybe I'm going to ask you, Alexander, regarding this point, what kind of question do you think in this point still not really answered? Or maybe for you start asking this question and you don't know the answer. Or maybe still missing for you. I don't know. What kind of things you think is still missing here, or questions not answered?
Yes. Yeah. So I think in robotics, there are so many exciting research questions that I still wake up about, super passionate about every single day. The one question that I really love to think about is how we can develop a robot, a learning system that over time can continually learn how to perform its task. And it can tell us, the human, there's some feedback back to us on how well it understands this task. Right now, the learning of many robotic systems and machine learning systems in general is kind of almost one directional. We provide the system, the algorithm, some training data, and then we train this algorithm and then we deploy it. And it's just a straight shot through the pipeline. But what I'm really interested in is how we can develop more of a feedback loop, a cycle, and how we can have robots that not just take the training data that we require, but maybe looks at that training data and can understand where it needs to focus on. What are the pieces of the puzzle, this problem, that it really needs to pay attention to, where it shouldn't be trusted, and maybe to train itself to really focus on this area because currently it can't be trusted there. So to have that kind of self-recognition by the machine learning algorithm is a huge question, open question for me, but I think it's one that is extremely exciting in this field specifically because this is, in comparison to all of the many fields in machine learning, I think machine learning has so many different ways that it has touched society, right? And we're seeing that now, again, more than ever with some of these recent advances that are coming out. But one area where I think robotics stands out is that robotics has the impact to really touch right back to human lives. So robots, we envision the goal, the dream for many roboticists, including myself, is to have robots that can work together with humans, not really replace humans. But what I'm really excited about is having the two work together and having robots that can help us.
That's interesting. Maybe I'm curious to ask you, if we speak about this scenario, what could be other factors do you think still maybe we have to consider? For example, you mentioned, I think in most of the time, that how we can design these robots that be adaptable to uncertainty or be generic. And I think that's something we aspire to have this design for robots in such a scenario we didn't expect or anticipate. So for you, what kind of factor do you think still maybe, besides being generic or maybe adaptable to these uncertainties, what other factor do you think should be also considered in these scenarios to be working with human?
It's a really great question. So I think one really important aspect of this problem is actually, let's maybe first start by taking a step back and saying, when we talk about adaptable robots and robots that can kind of learn how they should learn, that's kind of the way I like to think of a lot of our research. Maybe they learn that they need to be more confident in certain types of scenarios, and how can they go out and collect data so that they can reach that level of confidence. What does that level of confidence often mean for robotics? I think that's a really interesting question of yours. And I think one area could definitely be just pure performance of the robot. Maybe the robot can detect that or understand that it shouldn't really be trusted. Its level of performance should not be trusted in this scenario. And maybe it should go out and collect training data there. I think another really interesting aspect, though, on kind of the parallel side of performance, a lot of times we only care about performance, but I think also one really interesting aspect is when a robot can understand when maybe its decisions that it's taking have some maybe underrepresentation associated to them. So in other words, it means that they have some hidden biases and algorithmic biases that can lead them to take maybe still in the opinion of the data set, maybe a reasonable decision, but not a fair decision. And I think that's a very, very interesting question, and one, again, that we research a lot in the work that I've done to really tackle this question. Number one, of how can we have robots that when they're training, can they identify these types of hidden biases and places where they're not necessarily being fair to their particular the particular training data sets and training demographics? Can they identify this in a way that humans don't necessarily need to tell the robot what those demographics are? And then obviously, once the robot can identify this, how can it go back and kind of say, how can I develop my algorithm and change my learning algorithm to mitigate these biases? So not just focusing on performance, which is really what a lot of machine learning and deep learning researchers and practitioners care a lot about. And by performance, I mean just increasing the accuracy, moving 1 percentage point or 2 percentage point above the accuracy, but focusing on bringing the uniformity of your accuracy, like so oftentimes accuracy follows this curve. We have very good average accuracy over the entire data set, but we may have very low accuracy on some parts of the data set. And these are typically called the underrepresented regions, out of distribution regions, maybe places of your training data that you don't have a lot of information. And how can we increase the accuracy across the board? Not just increasing the average, but can we increase the accuracy on the lower end of our distributions, and maybe even sacrificing some accuracy on the higher end, just to make sure that we have this level of fairness and uniformity. And I think for robots to be ultimately deployed, coming back to your question, if we want robots that can be deployed into society, interacting with humans, they do need to be, number one, performant. They need to be safe and execute safe actions with humans, but they also need to be fair. And I think that's a really huge open question for this community in general.
That's a very interesting point, and I think because some people have questioned about what kind of maybe the design of fairness. Because if we imagine this robot would be like a god for something, some people will say that, and I don't know. Have you encountered something like that? How we can design something that maybe fair? I don't know. Do you have any kind of solution you anticipate for that?
Yes, exactly. So I think, first of all, I don't have a gold solution, I would say, at this point, but we have a lot of really interesting works that try to break down this problem and solve a part of the problem. So I wouldn't say that the community, not just myself, but the machine learning community still suffers a lot from this problem of algorithmic bias and fairness. But I'm happy to, maybe for the audience, I can share just maybe one example of how we can try to identify biases and even develop a learning algorithm that can mitigate some of the biases in the system. So we actually discovered this algorithm in the context of autonomous driving, because in autonomous driving, maybe contrary to popular belief, we have a ton of bias in the training data that we collect. So there's probably 90% of training data for autonomous vehicles is taken under maybe very sunny road conditions, very clean camera conditions. But oftentimes, when we deploy our autonomous vehicle, we want it to perform very well on the other 10% or the 1% of the data that is under nighttime, very bad visibility, maybe it's raining, maybe there are some very tight turns and curves. And all of this data is underrepresented. So we can learn a robot that can drive in the 90% of the scenarios very effectively, but it's going to be biased, or it's going to have lower accuracy and performance on the underrepresented scenarios. So without telling this robot what it means to be underrepresented and overrepresented, can we learn kind of a level of confidence in these two types of scenarios? And what we showed was that we can actually build this into the controller of our model. So by having our controller try to do two things instead of one, not just control the car, but now maybe it also has to predict the likelihood of seeing that type of data in the data set, right? So if we think of what that means, it means that basically now the network or the model has to learn about not just the how to control the decisions of the car, but also how to make, or how to understand how this scenario that it sees right now fits into this broader scope of data that it's been training on. Now, if it understands that now this piece of data is coming from a very underrepresented region, we can feed this back as information to the network, and we can have this cycle back to the network. So now the network can kind of understand that it should pay more attention to these types of scenarios, because these are underrepresented scenarios. And if it just leaves them as underrepresented, we can do well on average, but not on these cases, right? So we actually showed this in autonomous driving. Then we applied this algorithm also because we realized that this has huge potential impact in other domains as well, in computer vision and facial detection. We took this same algorithm from autonomous driving and also applied it to these domains. And we showed some really extraordinary results. We showed that the algorithms can learn to automatically pick up on gender biases and racial biases in facial recognition systems. And in those cases, one really exciting thing that came out was that it was able to identify some biases that I think even humans, it would be hard for humans to describe that these detectors are biased towards those things. So one example of that, I think it's very obvious that these detectors have biases towards things like gender and race. But maybe one interesting thing is that we found that a lot of these facial detectors are extremely biased towards the use of sunglasses. So if a human is wearing sunglasses or not. So they do extremely poorly on individuals with sunglasses because, again, probably 95% of individuals are not wearing sunglasses in the data set, and only 5% are. So when you have that 5% of training data with sunglasses, the accuracy drops significantly. And that's a huge kind of hidden bias that would be very difficult for maybe a human to come in and think of that beforehand, right? But this is something that we're able to kind of automatically detect and then mitigate as part of the learning.
Excellent. So maybe I'm curious to ask you in that case about the intelligence to, or having common sense to recognize this kind of things in an efficient way. How do you see this kind of vision capabilities to have this kind of intelligence to, like AGI, for example? But maybe I'm not sure what kind of limitation these things still maybe we can push the capabilities here, and how you view intelligence so far.
Yeah, so I think this is one piece of the puzzle, right? So to have an intelligent system like humans, right? Humans are able to reason about these things like biases. They're able to reason about when they can't be trusted, but there's other parts of the puzzle as well, right? So if we talk about intelligence more broadly in robotics, I think another very important aspect is having a system that can kind of combine symbolic reasoning and reasoning capabilities in general with a lot of the learning capabilities that we have in conventional deep neural network architectures. And I think this area, again, is of huge importance. I think how can we combine symbolic and kind of common sense? A lot of people call this common sense. How can we inject this into the robot? Because now humans, and perhaps this is over many years of many generations actually of evolution, humans have developed this extremely powerful representation of common sense. And even from a few months after birth, we're seeing how young babies can quickly start to reason about some geometric physics properties in the world. They understand when they start to push the block towards the edge of the table that they know not to push it too far because the block is going to fall. And that's something that probably was only observed by those babies only a handful of times. Probably they were not observing this block falling too many times. They didn't need thousands of training examples. But just by understanding from other areas, they can understand these types of very common sense properties. And that's something that I think is another key building block for having these general intelligence robot systems that can operate in the world.
Mm-hmm. Great. So I'm curious to ask you in that case in robotics, I don't know how this is a relationship between the body and the brain we develop, because we speak about the embodied intelligence. Should we invest more in the body or the brain side? Should it be fixed or moving? Because you also work in soft robotics. So how do you view this question as well?
Yeah, exactly. I think robots are the study of body and brain, not just the brain. And we have to think about how we can develop also the body to be kind of adaptable, and how can we kind of create a good body for a given task. Especially when we think about some of the really high publicity robotics areas like autonomous driving, for example. The body is not really too configurable, right? We have a car, but it's maybe the sensors on the car are configurable, but again, there are like a pretty standard set of sensors that we put on this car. We don't really talk too much about changing the body in that case. But I think in the more general case, in my dreams, I can imagine kind of like the gold standard robots that can be created and constructed in a way that is adaptable, number one, and kind of forgiving, compliant to the environment, so that they can learn to accomplish these tasks much easier than a non-compliant robot. And I think the power there, again, is building a system that is, I almost like to think of it as you want to build a system that has some more specificity in order to produce some more generalizability. It's almost like contrasting thinking. So we want to build a robot that can accomplish or have like a specific set of physical properties in order to help it be more generalizable when it reaches the real world.
Mm-hmm. Great. So I'm curious to ask you, in this kind of research you're doing, sometimes do you have something that was counterintuitive, it doesn't make sense to you? Because sometimes you have this kind of something doesn't make sense. How is that happening? I don't know if you have encountered something like that.
Yeah, I think it happens a lot in machine learning for sure. Many times we have the machine learning algorithm do something that we as humans would not have really thought of, because these machines can, they're optimized in ways that humans are not, right? So the thinking process, if we call it thinking for neural networks, or what we can call it is maybe the optimization process for neural networks, is vastly different than that of humans. So I think because of that fundamental difference, we have so many things that can kind of emerge when we're designing these systems. I think number one is that how extreme, going back to the bias question, how extreme these biases propagate in systems. So neural networks are extremely powerful, and with that power, it means that they will pick up on any small details that you give them. And if those details contain hidden biases, then those neural networks are going to latch onto it. And I think to a lot of people, that can be very surprising, or maybe not the fact that they latch onto it, but I think the surprising aspect is the severity at which this propagates. So the bias in the data may very well be amplified throughout training. it may not be proportional to the amount of bias that we saw in the original training data. So even if we have underrepresentation by like 5% in our data, that 5% in the data may very well be a much larger gap when we compare it at the output, the decision making of the robot. And that, I think, is one thing when we start to see this in the community is very fascinating, number one, but it's also very eye-opening because it tells us kind of the power of these systems. They can really just start to learn any small thing that we give them. So we have to be extremely careful from that point of view.
Great, yeah. And I'm curious to ask you about the way you think about approaching a problem, because when I saw that the first time you introduced, for example, tennis sensor data analysis, and how you think about asking the right question and approach the problem and figure out that is the most significant maybe thing I have to consider in this problem. Because I think that's something, is important for students listening as well, how you approach this problem
A really great question. Yeah, I think in the case of the tennis sensor data analysis problem, for maybe the audience who's not aware, this is a machine learning project which tried to learn how to detect different types of inertial strokes. So these inertial strokes could be tennis strokes. They could also be different types of stroke, like for example, walking strokes, and then provide again feedback back to the human using this machine learning algorithm on how to improve their performance. So this is a very user-centric project. And I think one of the real inspirations for this project to me was that I really love to play tennis. And I think a lot of my the projects that I've really enjoyed working on have been projects that are projects that are about a topic that I'm very passionate about. It makes it so much easier for me to like really get excited and really devote 100% of my thinking towards solving this problem because it's fun. It really is something that is enjoyable to me. If you can find this intersection of what you enjoy and what you're capable of doing, I think to me this was almost the secret. I'm still trying to employ this technique more and more, and I think I still have a long way to go in designing projects and developing as a researcher in the scientific community. But I do believe that this is really important for all researchers out there. And that is really working on projects that you're passionate about, even if maybe the community is maybe not as passionate about those projects. So this tennis sensor data analysis using machine learning to detect tennis strokes, I was very passionate about tennis. I love to kind of collect training data on myself to train these algorithms. These are machine learning algorithms. And this project was done in 2010 or 2011. And this was far before like the AlexNet and deep neural networks kind of took off, right? So this was, I would say, before the boom of deep learning. But this was a very passionate project for me because I love to work with these algorithms. I love to test on them. I love to bring them back to the tennis court and help me give feedback. So, and that really motivated me to keep working on it, even though, and I think a lot of young researchers may feel this as well, that it's very, they almost feel pressure to work on problems that everyone else is working on. But I think it's very important to really find what you are really passionate about and work on those problems.
That's an excellent point, Alexander, because I think in academia, I don't know if you agree with that, there's a trend when you have a trendy idea, everyone is working in this idea. And sometimes if you really select something different, it could be risky a little bit. I don't know, how do you see that? Because you're in academia and you can see sometimes, I don't know if you agree about this view, but sometimes it depends what's the trendy thing, but depending on funding and grants. So I don't know, how do you view this point?
Yeah, so there are always, I think, two sides to the story, right? So one side, I can totally agree with you. I think a lot of benefit in the community comes from kind of diversity of ideas, right? So when two people are not working on the same problem and they really have maybe even different backgrounds. One person is coming from computer science, one person is coming from biology or physics or mathematics, and you can have different backgrounds can produce very different types of insightful research. And in that case, I can say that maybe I would like to see a lot more of that in the community today. I don't think we have enough of that. I would love to see a more interdisciplinary structure of the machine learning community and working on problems or working on solutions, maybe, not just problems, because I think the problems are very diverse. We have machine learning being applied to biology, chemistry, physics, all these different areas. But the solutions are kind of all grounded from kind of a much more narrow subset of the field. And I would love to see the solutions kind of diversify a little bit more and people working on more diverse solutions. But at the same time, I just want to present the other side of my thinking, because I do view this as a very gray area question. It's not just black or white. I think the other side is also very interesting because oftentimes, like you said, there's a question of funding. So it's much easier to find researchers to work on high-level problems that the community cares a lot about. Right now, that is machine learning and deep learning are really attracting a lot of funding. So from the point of view of attracting quality researchers, that's one point, right? So we need to consider that point. The other point is that the deep learning field has really benefited a lot from this really concentrated effort on the community to tackle this problem and really devote the entire community towards deep learning. I think for the past decade, there has been a amount of support behind deep learning algorithms and developing new deep learning algorithms, new neural networks that we have not really, I don't think we have really seen that before with any prior type of algorithm in the computer science community, where the entire community in like intelligence and robotics, I wouldn't say the entire community, but let's say maybe the majority of the community cares a lot about these questions. And I think to that degree, that has been extremely beneficial to the machine learning community as well. So that's not necessarily a bad thing. I think from that point of view, that has created extraordinary progress. It has made this field of deep learning expand beyond just computer science. Now it's being used in different disciplines. We're seeing it now impact biology and chemistry and all these different areas. So many areas that previously were kind of separate from computer science. They had computer science, but they were always maybe in biology. There were biologists who then tried to study computer scientists. Now we're having from the other direction as well, kind of computer scientists that are inspired by these ideas of biology and going to work on these very massive biological problems. And I think that has really been extremely beneficial to the community. So I do want to say that I think, yeah, there is kind of like these two sides to the story. But the way I do like to think of this is that you can find a place in the middle, right? You can find something that is in line with the community, like focusing on how we can use machine learning and deep learning, but maybe try to think with a different mindset than the rest of the community is tackling, right? So you can still try to advance the community without trying to just fit in this pool of everyone else.
So I'm curious, because we are working a couple of projects now, but maybe something very challenging. I don't know what kind of problem is still, it's very challenging for you.
Yeah, I think so. One thing that we do a lot in my work is take the deep learning models that we train in software and try to put them onto physical robots. And that's, again, something that is very unique to robotics. It's very different than machine learning researchers, because a lot of times, let's say in machine learning and computer vision research, we care a lot about data sets. So we collect a data set, maybe the data set is already collected for us, and we just have to achieve some good accuracy on this data set. But in robotics, that's only like half of the problem, I would say. The other half of the problem, to me, is extremely challenging and not always appreciated by the other sides of the community as much. So I think taking what we learn, like our neural networks, our models, the intelligence that we can learn there, and deploying it, putting it onto a robot is something that ultimately is kind of like the most important step as well, but it's also the most challenging step many times, because what you can learn in that step is maybe that your algorithm, your learning side is maybe not even totally optimized to the level that you were thinking, because real world robotics is ultimately so different than just operating on a data set. And yeah, that's a huge challenge. I think not just for me, but for the robotics community. But I empathize a lot with anyone who is suffering with those problems because I definitely suffer a lot as well.
Yeah, yeah, that's a good point. Yeah, to appreciate. But coming back to that lecture you do in YouTube, I think you're doing a really excellent job and make it accessible for many students. I feel that teaching, that's my perspective, teaching is very, very huge duty because you have to have this kind of, yeah, knowledge and also deep understanding and make it engaging. And I think you're doing excellent job. If you can share the experience in teaching and try to do something engaging for a student.
Yeah, that's a great question. I think teaching is such a rewarding experience. And one thing I learned with teaching has been that you may not understand the topics as much as you think you understand them until you have to teach them, right? So maybe you can think you really understand something, but then when you have to explain something to someone else, you realize how little you really understand about this topic. So teaching has made me really grow as a scientist, I believe, because I had to really push myself to learn a lot more. And the class that I teach at MIT is an introductory class. It's Introduction to Deep Learning. So it's not a very advanced class, but I believe that even teaching this class, there are so many subtleties of the field. First of all, it's a very broad topic. We cover so many different areas: computer vision, sequential processing, natural language processing, reinforcement learning, a little robotics as well. So it covers so many different areas, and having that type of or being comfortable to kind of tell students and about all of these different areas is something that really pushed my boundaries. I felt like I needed to really improve as a scientist in order to do that. So I feel like I benefited a lot from the teaching, and I'm so happy that I feel like the lectures have benefited others as well. So that's an extremely rewarding feeling that has come out of these lectures. And now what we're seeing is that at MIT, we started this class, I guess 4 years ago now. We started Introduction to Deep Learning at MIT 4 years ago. And since then, it has grown every year. Last year, we taught the class in 2021, and every year we teach it in the winter time. And we had over 700 registered students, and that made it MIT's largest class during the winter term. So it skyrocketed in popularity now, and that's again a very exciting thing and very frightening thing as well. But I think it presents amazing opportunities. So I'm so happy about that.
Doing really great job, yeah. But I'm curious to ask you, as a researcher as well, do you have a moment of doubt? Because sometimes we have this doubt, I'm doing the right thing, right direction. How do you deal with that moment of doubt, or maybe mistakes you did?
Yeah, all the time. I think this is part of research again. So I think with research, I would even argue that the research is not interesting research unless you have these moments of doubt. Because then it makes the problem almost more interesting, right? So like there's a question about if it can work. If you work on a problem which kind of the solution is obvious or naive, then maybe it's less interesting. I think there's a lot of really amazing research that is amazing because of its simplicity, right? So like sometimes we find some solutions or some algorithms that are beautiful because they're so simple, right? And those to me are my favorite papers to read. I love reading about other people in the community that can find these gorgeous algorithms, so elegant, that are so simple, right? And oftentimes I think those are the ones that are often hardest to find from the researcher's point of view as well. Even though they're simple, maybe it seems like it was very easy for the researcher to find these. But I think oftentimes it may not always be the case. So I believe that it's very common, even in those scenarios where you've come up with a very simple and elegant algorithm, to really doubt it and doubt what the meaning or the impact of your research ultimately has on the community. Because at least this is my experience, because I found that when I often try to tackle these types of problems, I may see kind of a simple solution in my head, before I tried to implement it. And then it turns out that there are some caveats and some hidden challenges that I don't foresee that makes this problem much harder. And that's so I think this is a very natural part of all research. It makes research exciting to me. I think this is the reason why I love to be a researcher, because I like working on problems that are exciting and challenging, right? So like problems that I have to even question myself if these are good solutions, if these are solutions that will impact the community more broadly, not just myself, but like the entire community. And I think that's one thing that really makes research so incredible. It makes robotics research especially, I think, because we have these connection of different disciplines from machine learning, computer vision, mechanical engineering, all of these different spaces. That is like something that is especially powerful in this space, I think, especially.
So since we close the end, I have a few questions. Maybe the first thing about what could be the tools do you think in robotics need to be, push capabilities for, or be still missing, or if you counter any like tools, this really need more, push here, or
Yeah, so in robotics, I think the main thing that we're seeing right now is the ability to train our robots in very safety critical scenarios, but in ways that is still safe, right? So just to give an example, in robotics, we may want to train an autonomous vehicle to avoid crashes, but it's very, very difficult to collect crash data of crashes, right? So that is something, by definition almost, if we want real crash data, that's not a safe event, right? So that means we're trying to collect dangerous events in order to learn how to avoid these dangerous events. So I think one tool that I'm also very passionate about has been the development of really high fidelity and photorealistic simulators for robots. And how can we kind of have simulators that can learn controllers for robots, which can automatically be deployed into the real world? And this is a huge problem in robotics, especially this question of sim to real. But I think with the proper development of simulation engines and tools for simulation, this problem can actually be much, much simpler. Maybe not solved completely, but it can be much, much simpler. So just as an example, one tool that we developed in our lab is a photorealistic simulation engine for autonomous driving. It's called Vista. And it is different than most simulators because Vista is data-driven. It does not use models of the environment. So that means that there is no predefined environments that the user has to define. All of the environments are built from the real world, right? So you can simulate your autonomous vehicle on real roads, right? So on real roads that look like the original road. So you can take it on, for example, Massachusetts Avenue in Boston, and you can build a simulation engine of Massachusetts Avenue, just as an example. And you can say, how can I develop a virtual autonomous vehicle to drive through Massachusetts Avenue, but using a different policy, have it crash into cars in simulation and do all of these very dangerous executions that we could not do on the real Massachusetts Avenue, but can we now do it in a simulated version of this street? And what we showed is that because Vista is purely data-driven, this is a data-driven tool built on real data of the real world, we showed that we can train now policies in Vista, completely in Vista, in the simulator, and have these policies be directly deployed into the real world. We actually demonstrated the first time an autonomous vehicle could be trained using only reinforcement learning within a simulation engine and then deployed without any changes onto the real world. And that was a really exciting advance because it showed that this tool of photorealistic simulation and ours specifically, again called Vista, is one that can be extremely powerful to the robotics community in general. We're actually planning now an open source release of Vista. Hopefully within the next few months, we'll be releasing a fully open source robotics platform for researchers around the community to use data-driven simulation to train their mobile robot systems and have these systems kind of have much more transferability to the real world. But I think more broadly in the community, a lot more focus on photorealism, rendering, and simulation can be extremely beneficial to the field of robotics.
I don't know if you can comment about soft robotics because you speak about that part, because I think soft robotics, the material perspective is really, if material is high nonlinear, do you think it's also data-driven here, or you still need this kind of physics-based, and how do you think for that aspect as well?
I think this is a really, really interesting area. So I think personally, I have not seen soft robotics simulators which are data-driven. I've seen some really impressive soft robotic simulators that can capture kind of like almost the physics on the particle level of the soft robot. And these are awesome. I think, but largely these are still very model-based. They're not totally data-driven yet. And I believe that is one of the things that is maybe challenging to the community, because we can develop policies for our soft robots in these simulators, but then there is such a large gap with these simulators for soft robots when we want to deploy them into the real world. And what that means ultimately is that the works that have tackled this problem in soft robotics to reality, for specifically the case of soft robots, the way they've overcome this is by making some extreme assumptions on the type of the robot and really constraining the problem in simulation such that this gap is smaller, right? So that they can ignore this gap to a greater extent. But I like to think of this problem almost from the other direction. I think, how can we, without making these assumptions, can we increase the data-driven part of this simulator on this side so that we don't need to make those types of assumptions? And then we can try to keep this small gap, but without the assumptions.
That's a good point also. Yeah, but I'm curious, two questions left, I think. First one, what could be the most important quality for you think is very important?
Yeah, so I think one quality that I like to push myself towards, I know I don't do this perfectly, but it's one thing that I really like to strive towards, is really being a very hard worker. So I love to my colleagues and to everyone around me, I really like to be known as someone who will really push hard on things that I'm passionate about. That can be research. It can also be things outside of research, like exercise and having fun. I really pride myself on having this quality of just being a very hard worker and devoting myself towards whatever I do. I don't really, personally, I don't like to do things unless I'm able to really commit myself to them. And I think this is a quality that I can definitely improve on. I think there's a lot of room to improve in this area, but it's one thing that personally I value very heavily. I think that this is a quality that I need to improve on more in the future.
Great. And lastly, I don't know if any advice you received that was life-changing, because, yeah, there's maybe advice you stick to in mind. Yeah.
Yeah, so my advisor, Daniela Roos, has a really great saying in the lab, I think, that provides me with a lot. First of all, she gives so much good advice, so it's hard to pick this one, but this one is kind of very common. She gives in the lab. Every time we have a meeting with her, she tells us to always keep the gradient. And what that means, in, like, for example, it has like some machine learning or optimization connotation behind it, right? So the gradient in machine learning is like the slope of the progress of the learning. But when she says keep the gradient, it means that keep trying to improve, right? So every day you have to sit down and tackle your problem, and always just try to improve off the previous day, right? So whatever, if you're having a bad day, actually, she doesn't say keep the gradient. She says first you have to change the gradient and then you can keep it, right? But in general, she always says keep the gradient, and that's something that always sticks to me. Whenever I'm approaching a new problem, especially, I try to always just have improvement over the previous day. And I would say actually that this advice has impacted me outside of research as well. So I think even in outside of academics and just in normal life, I think this really follows me around, and always just try to be better than the previous day.
That's very important. I don't know if you have any final words you'd like to say. Any final words you'd like to say?
Yeah, I think once again, thank you so much for inviting me onto this podcast. It's a huge honor to be able to speak with you today, and it was such a great conversation. I really had a great time.
Thank you, Alexander. I think you are a great researcher, and I really enjoyed listening to you. Very inspiring and wise researchers. Thank you.